Okay, so my name is Patricia Beach, and today I'll be talking about, I'm doing a whole series on computational problem solving, and the first episode is on the problem solving process as a whole. And the other topics that we'll be doing are debugging, abstraction, problem decomposition, number-based conversion, algorithms, search algorithms, sort algorithms, and recursive algorithms. So there'll be much more to come in greater detail. But for today, we want to talk about the problem-solving process as a whole. So here's the overview. We're going to look at Poya's approach. I apologize for my southern accent. Computer problem solving as opposed to just general problem solving. Look at some examples and then talk about in practice, what do we do? So how to solve problems. This is Poya's approach. This is a book from 1945, and it was written for math problems, but it was found to be applicable to computer problems. It is still widely identified as a standard for this field. So he breaks it down into these 4 steps: understanding the problem, dividing the plan, carrying out the plan, and then looking back. So looking back. So step 1. The biggest hurdle to solving a problem is to be able to identify what is the problem we're trying to solve. That's true in math, it's true in computer programming, it's true in life. So before you can find a solution, you have to be able to identify the problem. Whereas Stephen Covey would say, begin with the end in mind. So where are we trying to get to? So in terms of computers, or in math, if you're given a problem, a word problem or a project or a prompt, an FRQ, you have to be able to unpack the problem. Make sure you understand what the words mean. What are you being asked to do? You should be able to restate the problem. Can you draw a picture? Do some pseudocode. Whatever your tools you have to state the problem, understand the problem, make sure that you have enough information to solve the problem. If you're given incomplete information, you should be able to identify that and state it. Okay, Deepa is coming on soon. Good. After you understand the problem and you can draw it, tell somebody what it is, identify what you're actually trying to do, then you want to create a plan. So, how can we approach problem solving? Well, you need to apply strategies. So if you're doing a math problem or programming problem, you might want to think, have I done something like this? So maybe I'm doing a loop. Well, I've probably done loops in other projects, so let me go back and look at how that worked. Well, you know, if I'm doing a, let's say I'm creating a program to find the minimum in an array. Well, if I had done a program to find the maximum number in an array, maybe I can look at that and compare how they're similar and how they're different. So, you know, use the work you've done previously to help you. Look for patterns. So when you have some programming experience, you'll start to see problems that fit into certain patterns. So we're going to have a loop, or we're going to need to, this is a counting situation, or this is a summing situation. So you'll start to see patterns develop after some practice. Draw a picture. Show what the solution should look like. Draw a flowchart. do a storyboard, but do something to identify how you want to approach the problem. You want to break down big problems into smaller ones. So for example, if the problem is that you want to pay off all your bills, you would need to identify how many bills do you have? How much money does the total represent? How much money are you making? How do do the math and figure out how long will I have to work to pay these off? And there are a lot of little steps that you have to take to solve a big problem. So break it down. In computer science, we talk about decomposition. So this is a good example of taking a big, seemingly unsolvable problem and breaking it down into little pieces that you can solve. If you don't have a clue, take a guess. Try something. So if you don't know how to solve something, just use your best judgment. Okay, once you have a plan and you can have some kind of proof, now you want to carry it out. So apply the plan that you've created. See if it works, if you get the correct answer, and then once you have, look at your solution. Is it the correct solution? Did you meet the requirements of the problem or the project? Revise it. So you want to be in continuous improvement. So looking back, can you do it with fewer steps? Can you make the program run faster? So make it more efficient, but the most important thing here is to make it an effective solution. And then in the future, can you use this method for some other problem? So this is just a problem-solving process. I know I've been talking about computer programming, but really you could apply this to any type of problem, not just a programming problem. So now when we do get to programming and the computer, we have the computer problem-solving process. So still relying on Hoya's solution, but we're going to apply this to specific computer problems. So the computer problem-solving process is made up of 4 phases. They are similar to what we saw before. The first part is analysis and specification. So this is, once again, identifying the problem. You have to understand what you're being asked to do before you can do it. And then specify the problem that the program is meant to solve. This is the specifications part of our project development. So before we ever touch the keyboard, before we get into a specific language, we have to understand what the problem is. So if you're a student in a classroom and you're being asked to do some kind of mathematical problem or build a game or solve a math problem, you need to understand what you're being asked to do. So once again, understand the problem. This cannot be stressed enough because a lot of times most times, students and professionals, they want to dive right into the programming, but if you build your program on an unstable foundation, it's going to be really hard to maintain down the line. So you want to be sure that you have a clear understanding of the end result before you begin. So what do we do after we know what the problem is? Then we start to build an algorithm to solve it. So remember, an algorithm is just a logical sequence of steps that we can use to solve a problem. We're still not talking about code. We're just talking about developing an algorithm, developing a solution to the problem. And then test the algorithm. This is a good place to use flowcharts, pseudocode, storyboarding, just to make sure that you haven't left any holes in your solution. Now, the problems we're working on with the students are relatively simple, but if they get in the habit of using these techniques now, they'll make better programmers if they're become college student, computer science students, or if they go into programming as a profession. After you have a working algorithm, now it's time to implement. This is the first step in this process where we're going to touch the computer code. At this point, you should be able to take your algorithm and put it in any appropriate language for this problem. So this is the first time we're getting into coding. So we'll translate the algorithm into a programming language at this step. Once we've written it, then we test. So we have the code, test, loop. We code, we test. This is where you might get into different development schools of thought, either with a quick loop or then a long loop. It depends on where you're from and what the standards are. But it's good to get something working, test it until we get the right result. After we have the correct result, we implement our program or our code, our system. We'll enter the maintenance phase. So this is where it goes into use. We'll continue to maintain and improve it as changes are made. Either the specifications change or technology changes. Lots of things can change that cause us to have to make changes to the program. Data formats can change. So this is a constant process, a constant loop. And a lot of times you'll see it represented as a circle because really it keeps going. And you can relate this to the kids in terms of game development. They wouldn't expect to get stuck in one version of the game. They would expect that game to continue to improve over time. So the same thing with their programs. We want to encourage them to have a correct solution and an efficient solution to be able to build it in advance, to create the solution, create the algorithm for the solution before they actually code it. And there are a lot of ways to do that. You could have one team swap their specifications and have another team build it. Of course, you can do the peanut butter jelly algorithm game where you do exactly what they tell you to do. So just make sure that they are doing the work on paper before they jump onto the computer. Okay, so here are a couple of simple solutions to a sample problem. You'll see this in every textbook in every language. So it's a beginner program. The instructions are to write a program that asks the user to enter a temperature in Celsius degrees, and then the program will convert the temperature to Fahrenheit and display the results to the user with the appropriate message. And then we even give them the algorithm here, so they don't have to go find it. They're given the correct algorithm. And I've done solutions in Scratch and Java, just for comparison. Okay, so here is the program in Scratch. The cat asks to enter the temperature in degrees Celsius, and when the green flag is clicked, the input statement runs, and the algorithm is programmed here using multiple mathematical operators and expressions, and then the output statement concatenates the answer here. Answer. This is the original Celsius. That it says Celsius, and then this would be the Fahrenheit. So it's going to show the original Celsius is equal to however many degrees in Fahrenheit. And I have a link in here. I'll run it for you in a second. Here is the Java version. So same problem, but this is the Java solution. So in this case, we have to have do our own, make sure we have our libraries imported. We have to have a class, and we have to have a method. We have to have variables declared, and then we get our data from the user here, and we do here's what we prompt them for the data, then we collect the information and put it in the variable for Celsius, and then we calculate Fahrenheit, and then we print out the concatenated result. So once again, we have Celsius, however many Celsius degrees, Celsius equals however many Fahrenheit, calculated degrees, Fahrenheit. So real simple, but there's a lot to it. So having this as an example helps them go through a lot of processes. So they have to understand that they're getting user input, that they have to ask the user to input, that they have to do some mathematical conversion, they're using variables, and then they're using string concatenation and output. So a lot of little pieces, and a lot can go wrong in there. One of the common errors is they'll do the opposite conversion, or they will label it the opposite way. So a lot of room for learning and teaching in these examples. So what tends to happen is students get mired in the details. They get overwhelmed, just like in math. When they see a wordy problem or a mathy problem even, they just say, what am I supposed to do? What am I supposed to do? So you have to help them read through, make notes, underline, circle, help them use strategies to identify what am I being asked to do? What do these words mean? What is it implying here? Is it looking for an array? Is it looking for a loop? Is it implying that I should use integers or doubles or etc.? So just help them understand what they're supposed to do. Encourage them to draw it out, make pictures, diagrams, etc. Use flowcharts, use pseudocode. I require my Java AP students to do everything on paper before they touch the computer. Here. Explain what you're being asked to do. Always talk to somebody. We're going to get into that in the next episode when we talk about debugging. But if you're reading something and don't quite get it, always, when you try to explain it to another person, a lot of times it'll help you understand. I find for myself, and I try to get my students to take that approach. And then finally, apply the information processing model. So when you're looking at creating a solution, think about what are your inputs, what are your outputs, what's the processing going to be doing. So in our case, we were being asked to convert from Celsius to Fahrenheit. And then there's their storage. We didn't have storage, and we don't have a lot of storage in these courses, but we can talk about the variables as storage or arrays. Okay, so here, if you have any questions or comments about this, if you could see something we're missing, how to improve it, if you have any stories to share from the classroom, you can make those comments on EdWeb at this point, or email me directly, or get in touch with our group. So this is just part 1 of 10 webinars on this subject. These are the sources that I use for this. The textbook is the Computer Science Illuminated book. This is a good book that goes along with CS Principles. It goes through computer science in terms of layers. There's a good website, How to Solve It, which will help with solving any kind of problem. This is the website about George Boya from Wikipedia. Here's the Scratch example that I had shown on the slide. And then just for your information, I use this JGraphs Java IDE, and you can download that for free. It's written by Auburn University. And the reason I like to use this IDE particularly is that it doesn't do code hinting. So the students are relying on themselves to come up with their solutions, to come up with the right commands. It doesn't pop up the command for them. And that is all. Thank you. Okay. Hi, my name is Patricia Beach. This is episode 2 of the Computational Problem Solving Series, and we're going to talk today about debugging. So, what is debugging? Here's an overview of what we'll be covering. What is a bug? Who's Grace Hopper? How can you help students learn to debug? We'll look at some strategies and examples, and then talk about debugging in practice. So, what is a bug? In computer science, a bug is not actually a critter. It's defined on Wikipedia as an error, flaw, failure, or fault in a computer program or system that causes that system to produce an incorrect or unexpected result, or to behave in unintended ways. There is some controversy. If you do a search on computer bug, you might find that some people don't like this term because it implies that it's an external factor, where really computers and programs are built by programmers and computer engineers. So the bugs are built into the system. It's not something that creeps in and wreaks havoc on your program. It's a weakness in the program itself. So our job as programmers is to try to build strong programs that are resistant to these types of errors, and when we do have them, to be able to use strategies to find them and fix them. Okay, so this is an example. This is a picture of the first actual bug that Grace Hopper documented on September 9th, 1947. This is from the website. I have the link at the end of the slides. It's called A Day in History, computerhistory.org or something like that. So I like to talk about debugging during Computer Science Education Week because that's the time where we talk about Grace Hopper. We celebrate CS Ed Week around her birthday, and it's a good time to remember her role and her contributions, and the kids get a kick out of the bug, and it works well as an activity during Computer Science Education Week. So we remember Grace Hopper because of the bug. That's a minor thing. She developed COBOL. She helped demystify computers. One of my favorite things that she did was she would demonstrate the length of a nanosecond with a piece of wire, and that demonstrated how long it took a nanosecond to travel through the network. So some of the things that we struggle to do with our students in terms of demonstrating these abstract concepts, she was doing on in speeches and on television, and she really helped get the word out that made computer programming and computers more of a normal person thing. She felt like computers should be accessible to more than just uh, physicists. That you should be able to work with computer uh, with English. So that's how we got COBOL. She was instrumental in COBOL and the languages that preceded COBOL. And that's kind of our first high-level language where we use English to, and not a machine code to talk to a computer. And she's just a great female role model. So this was a Google Doodle from her 107th birthday, I think. So how do we help students learn to debug? Well, when you're teaching, I find that you have to expect, it's a tough thing to teach. And, kids will put in something and then they'll immediately, they say, I don't know what I'm doing. This isn't working. So you have to really hold their feet to the fire and encourage them and help them get to the right answer. This information is derived in large part from an article I've credited at the end here, Sheena Vaidyanathan, and I like the way she puts this in graphical format, so I included it here for your benefit. We want to help the kids without just handing them the solution. So we want to make them work, we want to make them, encourage them to struggle, and later, encourage them to fail. But we do want them to succeed, so they keep trying. So depending on the kid, we'll get to the teacher's role next, but we want to give them steps to try. So before you ask me to just give you the solution, review the problem. So back to our problem solving steps. Make sure you know what you're trying to do. What is this program supposed to achieve? And they should be able to state that. And then, what is actually happening now? So what's working, what's not working? What did you do? Did you make a change? Have them go through these steps. If you're trying to do something new, if the goal of the project is to do something new, what have you done that's similar to this? Go back and look at other programs you've written. Okay, maybe you're trying to do a for loop and you can't remember the syntax, or it's just not working. Go look at another program where you did a for loop and see how that one worked. So look at your own stuff. If it's similar but not quite the same, look back at your textbook or your course material that's online. So look for examples that can help you. Okay, Deepa's router is down, so sorry we missed you, Deepa. But you can watch this in the future. Require that the students use their debugging strategies and tools. So we'll look at those in a little bit. When you're making changes to a program, just make little changes. Don't go and change 10 different things and then expect it to continue to work as before. Make little changes, save and try as you go. When you're trying to debug, or when a student is trying to debug, they should talk about it. Don't just ask somebody, hey, how do you do this? Give me the answer. But explain the problem to your buddy. Talk about these things, what's working, what's not working, and usually talking about it will help reveal the answer, because if you can understand enough to explain it, most times you can then see the problem. After a student has tried everything on this list, then if they still are stuck, then ask the teacher for a hint. But don't start by just saying, I don't understand, which is the default posture for some kids. But try to work with them. Now, as the teacher, here's what I try to do. And this is from the article as well. So after the student has tried all those steps, then go over and ask the student to describe what's happening. But usually, if they can tell you what's happening, this is what I did, now it's broken, etc., they can usually figure out the solution. Sometimes, before I can ever get to a kid, they have figured it out. They'll have their hand up and I'm helping someone else, and by the time I get over to them, oh, I got it. If they are still stuck, ask them, have you followed the steps outlined on the previous slide? Have you done all these things here? If they haven't, make them do it. If they are just completely lost, or they have genuinely tried and they still don't have the answer, then depending on the student and depending on their level, help them, coax them, guide them, but our goal is to get them here. Make them feel like they found a solution, either on their own or with your help. Not, oh, here you go, I gave you the code, or here you go, I'm just gonna quit. So we want them to eventually reach a working solution and feel good about themselves, so they'll continue programming and continue problem solving. I just feel like computer problem solving leads to good problem solving throughout your life. These are some examples and online locations of some debugging lessons. I love Scratch, my first programming language for most people, no matter how big or little they are. If I have someone who never programmed, I'll start them off with Scratch, just because I like the way you get that graphical feedback. So if you go, there's a studio that is developed by Scratch Ed. This is Scratch Ed here at Harvard. And they have a whole ton of resources here outside of Scratch itself. They have a collection of common bugs. This debug it. This is the studio. They have these strategies, kind of like what we've talked about before. Discussion forums about Scratch, tutorials on Scratch, etc. So this is somewhat for the teachers, somewhat for the students, but this is a great resource. Scratch Ed is for teachers to use in the classroom. This is the actual Scratch Studio with all the debugging examples on here. So you can see they're numbered 1.1 and 1.2, 1.3, etc. So let's take a look at 1.1. In this case, the cat is the cat and the gobo are supposed to be dancing, but when we click the green flag, only the cat is dancing. So how do we fix the programming? So this is part of the creative computing workshop. I like to use this for camps or for teaching at the library, things like that, or teaching very young kids or kids who have never been on the computer. This is a great resource. It's available through Scratch Ed. So now the kids can look inside and we see the cat's code. And if we run that code, we can see what the cat does. And then we can go over to Gobo and we see Gobo's code and we can say, hey, what's different about that? If we click it, what happens? Well, it runs, but what's missing? And so the very youngest kids can figure this out. So we're missing that one event handler. So it's a good way to talk about debugging. It's a good way to talk about event handlers and just give them some ownership. And there's the whole series on that studio to try. Khan Academy has this debugging guide with some good. This is kind of a broad strokes for any programming you're doing. Um, kind of reiterates what we've already talked about. Ask the student to read the challenge stuff aloud. Look at the hint code. So if you're on Khan Academy, they do have hints. They get fewer hints as you progress through the curriculum. Ask them to explain. What's it doing now? What was it doing? Encourage them to try something and see what happens, etc. If they don't understand. So they go through here. This is for challenges. This is for projects. This is for error messages. If they don't understand what their code or the starter code is doing, trace the code. Go line by line and trace the code. That's my favorite debugging tool, is tracing the code. Now, this is the debugging lecture from CS50. If you're not familiar with CS50, it is a free online course from Harvard. I recommend it to everyone. It starts off with Scratch. It goes into C to show you how programming is at a lower level and how difficult it can be if you have to take care of everything yourself, and then moves you into Python. It's challenging, it's doable, it's the most popular course on campus, they say, and they're going to be coming out with a game development course soon. So they kind of, I don't think they invented rubber duck debugging, but they have popularized it. And here's my little rubber ducky. And the purpose of the rubber ducky is that you can explain your problem to him. Even if you don't have a partner, you can explain your problem to the rubber duck. And by virtue of just expressing your problem, you can help yourself find a solution. I will click on this and play just a couple seconds of it so you can see what it looks like. This is him describing Okay, so you can see where he's going there. It seems silly, but just talking through the problem will help solve the problem. So these are popular. If you sign up for CS50 for your classroom, there's an AP version, and take part in the puzzle day. They will send you a whole kit, including the rubber ducks and stress balls and some t-shirts and other things. So take advantage of those resources. And there's a wiki page that goes with this rubber duck debugging. This is a link to the Think Like a Computer Scientist about debugging. So they have a whole appendix on debugging. It tells you, the difference between compile and runtime and logic errors, which is important, and so on. So this is, I won't go through this all, but this is a nice little appendix on debugging. And then finally, these are the kind of things that we encounter in practice. Students blame the computer, the internet, their dog, everybody except themselves in some cases. I have gifted and smart and highly intelligent kids, but the minute something breaks, they immediately blame the internet. Oh, something's broken. So, you figure out who those kids are and help them review their code more carefully. When I demonstrate code on the board in Java, in Scratch, in robot language, whatever we're doing, I trace the code. I can physically trace it if we're doing something like a robot, pseudocode, by walking the square tiles on the floor, and I'll have the students direct me. But if we're doing written code, I trace everything, and that means I set up my variables on the board. If it's a loop, I show the loop, and I encourage the kids to do it. I feel like there's no way you can possibly interpret code without tracing it. And, if it's a kind of a little bit more nuanced bug, you really need to get in the habit of tracing your code in order to see that. Teach the kids to look at the errors. Read the errors. Most of the time the error report will tell you what the bug is. Now, there are many instances where the line that's reported in the error report will be after where the error was. So maybe if I leave a semicolon off on line 9, I might get an error on line 10. So you'll get used to that, and teach the students to look for those kinds of things. So it might be reporting on one line, but the error is caused by a problem on the previous line. Once again, talk it out. Explain the problem to your partner, or your rubber ducky, or draw a picture, prevent errors by planning, pseudocode it, flowchart it, storyboard it. Make sure that you have built a good solution before you start building buggy code. Another thing that is worth mentioning here is just documentation, documenting your code, indenting it properly, naming variables with reasonable names, naming methods and procedures with reasonable names will help debugging. Sometimes you're debugging somebody else's code, so those kind of things will be really handy to the people who are going to be looking at that in the future, even if it's you. Okay, if you have any questions, comments, improvements, please respond on EdWeb. This is the second part of the computational problem solving series. This was debugging, and the next episode 3 is going to be over abstraction. Thank you very much. Goodbye.